Okay, so last time we talked about we started talking about memory allocation, and I introduced some assumptions. So just to remind you that in the pictures, I will show, like, I'll assume that each block effectively that you see here is not 1 byte, but it's actually a word, right? 4 bytes for 32-bit CPUs and 8 byte for 64-bit CPUs. Well, except when I mention explicitly that it's 1 byte. So we'll also looked at some examples when we allocate a certain number of bytes. We also discussed, certain constraints that memory allocator should have, and specifically, like the fact that we cannot do compaction after we allocated memory. So, for example, if we realize that 2 bytes better to be placed at the very end, because let's say the following request after P4 malloc 2 is 5 bytes, that's too late. We cannot change it. So that's the assumptions, right? And there are other assumptions that we cannot postpone malloc requests. We have to immediately respond and so on. So let's look at specific goals that we want to achieve. So clearly, one of this goal is a performance goal. So we want to make sure that malloc is as fast as possible. So let's say given some requests of malloc and free, R0, R1, and so on, our goal is to maximize throughput and peak memory utilization, right? So and what is throughput? So throughput would be the total number of requests for both malloc and free typically, right? So, I mean, unless you want to have throughput for malloc and free separately. So for example, if you have 5,000 malloc requests and 5,000 free requests in 10 seconds, we have to count both malloc and free. That's going to be 10,000 requests in 10 seconds. So therefore, we have 1,000 operations per second. That's probably very slow throughput, but that's just as an example, right? So yeah, so you definitely want to have much faster memory allocated on this. Yeah, so okay, but the goal of maximizing the throughput and the goal of maximizing memory utilization, they're actually conflicting typically. For example, here I can probably maximize memory utilization if I put 2 bytes at the very end, but that can slow down things when I want to find the right block for the memory allocation. So that can make malloc slower. So, and vice versa, malloc can be faster, but not necessarily great in terms of memory utilization. So the second goal is the peak memory utilization. So the first one was throughput, and now we want to have memory utilization. Again, we want to have both. We don't want to have just fast memory allocator, but the one that wastes memory a lot, right? Or the one that is very efficient in terms of memory, but works so slow that it's completely useless. So we want to find something good in both goals, right? So, and again, there may be different priorities, different weight you can give to each of this goal, right? So there is no sometimes there is no clear answer which is more important, right? So, but that's something that we have to decide for our particular application. So given sequence of malloc and free requests, right? So R0, R1, RK, and so on, right? So again, we don't care which request it is. It can be malloc or free, we count both, right? So let's define an aggregate payload. So what is an aggregate payload, right? So remember that malloc has a size t size, right, that you supply as a parameter, right? And it allocates a payload of p bytes. So now after request RK has completed, the aggregate payload PK right? So remember, we have requests R0, R1, and so on, right? So now for the payload PK, we'll define it as a sum of the current allocated payloads. So let's go back to our previous picture here. And yeah, so let's look at this example. We have P1 malloc 4, that's R0, request 0. Then the next one is R2, then R3. Then free P2 is going to be R4. And then finally we have R5 for malloc 2. So what is the aggregate payload P5? So that means when we have request R5 completed. Okay, go ahead. Yes, 12, right? So we will find the sum of all these payloads that we have so far. So that means 4, 2, and 6. So again, the definition is that, malloc results in a block of payloads of p bytes, right? So after request RK has completed, the aggregate payload PK is the sum of currently allocated payloads. So we'll have to find the sum of them. So how is it different from the heap size? So what is the heap size here? So we have 12 bytes allocated, right? And how many free blocks? How many blocks? We have five free blocks, right? So what is the heap size then? 17, right? Am I correct? 17 bytes. Yeah, so that's our current heap size. But we will also assume that the heap can potentially be expanded. So maybe right now we have 17 bytes, but later we realize that this heap is no longer sufficient. So maybe we're trying to allocate some large block after the last request and then realize we don't have any space anymore. So this is when we have to expand the heap. So I will assume that the HK is monotonically non-decreasing. So that means the heap can only grow, right? So just for simplicity. I mean, it doesn't have to be in real life, but let's just for simplicity assume that it's monotonically non-decreasing. So now, let's just kind of look informal before giving a formal definition, right? Let's look informally. We allocated 2 bytes at the very end. Let's imagine that we have another request when we want to allocate 5 bytes. So what would be the minimum heap size at that point? So it seems like I cannot fit it in 3 bytes anymore, right? So that doesn't work. At the very end, I have 2 bytes. So if I want to allocate 5 bytes, I want to expand my heap at the very least by 3 bytes. Probably in practice more than this, but at the very least by 3 bytes. Yeah, so now the heap size will become 20 bytes, right? So let's compare that with another possibility. Let's say we had this last line P4 malloc 2, and we allocated this 2 bytes, in the middle block, right? So what if we did something different and allocated at the very end 2 bytes? At that point, we would still have 5 bytes available for the following requests. So we would still be able to accommodate all these blocks by using a heap size of 17 bytes, right? So we still have the total payload, 12 plus 5 is going to be 17 bytes, and we can accommodate it in 17 bytes heap. That's ideal, right? So that's like 100% of memory utilization, right? So we are not wasting any memory. On the other hand, in the second case, like when we have to expand the heap, we have to increase it to 20 bytes, even though the aggregate payload is 17 bytes. So now it's no longer 100%. So we waste some memory. So yeah, this is the definition. So peak memory utilization after k+1 request is going to be the maximum payload, right? So from y from 0 to k divided by hk, right? Because remember that heap is monotonically not decreasing here. So yeah, so this is how we can define this, right? Again, just an informal definition is how much memory we would waste, right? Just remember that. So we have two possibilities, and in one case we have 100% memory utilization, in the second case we don't have 100% anymore. Okay, so poor memory utilization caused by fragmentation. So what is that? So any idea what this fragmentation is? Like I had like external, well, first of all, what is fragmentation? And the second, what is internal and external fragmentation? Any guesses? Like what is fragmentation? Okay.
Just having the empty spaces between each memory.
Yes. So that's one possibility. Yes, so certainly, right? Yeah, so what is the name? Like, do you think it's internal or external fragmentation?
It's internal fragmentation.
Okay, we'll get to this. Yeah, so yeah, anyway, yeah, so yeah, so just yeah, so in general, this is correct, right? So we have, I mean, aside from internal, external fragmentation, but the idea of fragmentation is that it seems like we are not using space efficiently, right? So we are having some fragments, like we have put 2 bytes here, but then we have a small fragment of 3 bytes, then yet another smaller byte, 2 bytes, all these things. Basically, all our free space is divided into smaller fragments that becomes unusable, right? So we have some free space, but sometimes we cannot use it because it's too fragmented. Okay, so there are two types of fragmentation: internal fragmentation and external fragmentation. So for internal fragmentation, so what is the internal fragmentation first? Remember that we have payload that we have to put in a block, but we have some potential overheads. So for example, we have to sometimes keep the size of the payload, right? And we will get to that in the moment, right? We have to have some padding for alignment purposes, so we have to waste some space, right? Or maybe we deliberately want to allocate a larger block than our payload because of some policy, because maybe we decided that user allocated 10 bytes, but then maybe very soon the user is going to call reallocate with 20 bytes. So why wouldn't I allocate 20 bytes right away? So maybe I will improve performance by doing that, or maybe I will improve memory utilization by doing this. So that results in internal fragmentation. So it seems like we have a block, but we have some overheads inside this block. So that said, it only depends on the pattern of previous requests, and therefore it's easy to measure. External fragmentation is something different. So for external fragmentation, we looked at the example with 2 bytes. Let's look at another example when we allocate 4 bytes, 5 bytes, then we allocate 6 bytes, then we deallocate 5 bytes, right, that we previously allocated in step 2. And now we are trying to allocate 6 bytes. It looks like we have space for 6 bytes in total, but we cannot feed this payload anywhere. So therefore, we have to expand the heap. So we have fragments, but they're not contiguous. So in general, it's very hard to predict. I don't have a crystal ball to see what other malloc requests going to come in the future, right? So, and typically at the compile time, we cannot determine that only at runtime when we call malloc, we can just see like on each tab, but I cannot go and see what's going to happen in the future. I mean, perhaps if I knew that 6 bytes are going to come later, I would have arranged like the allocation differently, but it's too late at this point. So therefore, it's kind of difficult to measure because it depends on the pattern of future requests, and we cannot predict future. So external fragmentation in general is actually, I mean, it depends on the application, but in general, external fragmentation is a bigger issue than internal fragmentation. Any questions so far? So does it make sense? Like internal fragmentation is within the block, external fragmentation is across different blocks, right? So we have, like when we look at our entire heap. So we have some space, but we cannot fit the payload anymore. So in fact, like in the past, I don't know if you used maybe your computer back, like, I don't know, like some time ago, right? So there was like a defragmentation tool for, you could defragment your hard disk. So for a somewhat similar reason, right? So you would move things around so that, because whenever you have some contiguous chunks in your hard disk, it's going to work faster. So that was an idea, right? So you would run this tool and it would move things around. Okay, so how do we know how much memory to free given just the pointer? So I guess I gave some hint already, right? So that we will have to keep a size, right? But in general, yeah. So we have to solve that problem because remember, for malloc, we have size argument. For free, we don't have size argument. We only have a pointer. So how do we keep track of free blocks? So there are some allocated blocks, there are some free blocks. How do we keep track of free blocks? That's another issue that we want to solve. So how do we pick a block to use for allocation? Many might fit. And then again, here, there's so many strategies. It's not the only possibility to allocate like 5 bytes after 4 bytes. I can allocate it at the end. I can allocate it in the middle. So, I mean, I allocate it after 4 bytes, but that's not the only approach. So what do we do with extra space when allocating a structure that is smaller than the free block that it's placed in? So for example, here, I guess here we don't have that, but maybe in the previous example, when we allocated 2 bytes at the very end. So what do we do with this free block of 5 bytes? So there are different strategies. Maybe we can dedicate the entire free block to this 2 bytes and use 5 bytes block for this 2 byte payload, but maybe we should, maybe we should split this free block into multiple pieces and have that remaining free block in the free list. So and how do we insert free blocks? I mean, clearly we have to put it in some sort of list, but again, that's the question that we want to solve, right? So how do we place it back? So let's look at the very first problem. So how much we need to free? So that is a fairly straightforward answer to this. and there is a standard method, right? So what you can do, you can keep a header just before the payload. So the payload is the pointer that malloc returns, right? Just before that pointer, you can dedicate, just before the beginning, right, of this payload, you can dedicate extra space where you place a header, and in the header, you're going to keep size. So for example, remember that each block is 4 bytes in this picture. So malloc requested 16 bytes, right? And I'm gonna keep also a header, and for that I'm going to use one extra word. So now I'm gonna have 20 bytes, right? 16 plus 4 is gonna be 20 bytes. And I'm gonna record the block size in the header itself, right? So the block size will contain the payload size as well as the header size itself, right? So yeah, so that's one possibility to do that. So now what can you do with, how can you get the header? Is there any easy way to do that? Because remember, in free, you also pass a pointer to the payload. So how do I get to header from there? So let's say I'm finished malloc, that's fine. I return the payload pointer, that's fine. But now I'm gonna call free. So how do I determine the size of the block? Well, I need to get to the header. But how do I get to the header from the pointer that was specified to the free call? Any ideas? Okay, go ahead.
Would it be like pointer -1?
Yeah. So, well, assuming that a pointer is a word size, right? Like size t star, right? So then you're gonna have -1. So it's gonna be in general. You have to subtract number of bytes that you have for the header, right? Okay, go ahead.
So that means you can only store up to one word less than how much the block size is. And so you have this one block for the header field.
So what do you mean one block less? Well, yeah, so you have to waste extra space for the header, right? Is that your question? Yeah. Yeah, so so what kind of fragmentation that increases?
External.
Well, this is going to be internal fragmentation, right? This is overhead. Right, so let's look one more time, right? So internal fragmentation is like overhead, right? That we have alignments, like sizes, whatever we have, right? Inside the block, right? Inside this particular block, because block becomes larger than it should be, right? But then external fragmentation, that's inside the heap across different blocks. So just because I didn't arrange blocks in the optimal way, right? I have that external fragmentation now. So yeah, so it's gonna increase internal fragmentation somewhat, but so there is also some strategies you can use to reduce it. I mean, it probably matters for smaller blocks. As soon as the block becomes larger, that overhead is negligible. Okay, so okay, let's look what happens here. So we have malloc 16, we have 20 bytes in the header, right? So this is why we put 20, because we have extra 4 bytes for the header. So it doesn't make sense, the previous one, right? So we will just keep the size inside the header. And the header is going to be adjacent to the payload. So now we have to keep track of free blocks also. So that's the second issue that we need to solve. Well, it's actually, I'm gonna kind of describe the approaches and also the project, right? So simultaneously, right? I guess those things are also related because for the project, you're going to be trying to get a good memory utilization and good throughput. And for that, you have to choose the right data structure and the right approach. Well, the first method that your textbook, CS app textbook describes is implicit list. And in fact, it even provides you a pseudocode for that. But please, in the project, don't copy and paste that code, right? please, you can use it as an inspiration for the implementation, but don't copy and paste. And for multiple reasons. First of all, for academic integrity reasons, right? You don't want to copy and paste. But second reason is that it's for a 32-bit CPU, whereas we are going to use 64-bit CPU. So you at least need to understand what you need to change there, right, in this code. So don't blindly copy and paste that. So you have to at least study that code and see what's going on there, and then implement your own code. But again, you can use it as a starting point, as some sort of inspiration. And the other reason is, I guess the most important reason is that it's not going to be giving you also good grade, right? So because it's going to be it's going to be bad in terms of memory utilization and throughput. So it's going to be okay, if I guess, for a checkpoint, but not for the final version. So therefore, you want to implement something better than this. So just a note about the project, right? So yeah, so some of you will ask it certainly at some, well, can I use this code? Well, you cannot copy and paste it, but you can use it as an inspiration from the textbook. But again, it's not going to give you a good grade, but at least what you can do, you can try some more complex approaches initially, right? If you are running late before the checkpoint, right? So you can kind of fall back to that approach, right? If you cannot finish in time, right? So that you can kind of continue after the checkpoint, right? So, but you can also find that it's better to start implementing a better memory allocator right away. Okay, so there are different methods. So one method is implicit list, and that's exactly the method that the textbook provides. And as you probably can guess, it's not the best method. It's not going to result in good performance and good memory utilization. But you can use it, right? So for simple memory allocators. So the idea here is that we don't distinguish between allocated and free blocks. And we don't really have any list that we keep. I mean, we don't have any explicit list for free blocks. Rather, we just iterate through the entire heap. We go to the very first block. Now we know the size of that block. So therefore, we can calculate where the next block is, go to the next block. That next block can be allocated or free block. So we're gonna go after this block to the next one and so on, right? So whenever I want to allocate, I'm gonna be discarding all allocated blocks. Of course, I cannot allocate it again, right? So if it's already occupied by someone. So, but I'm gonna be looking at free blocks, and if hopefully the size matches or at least greater than what I'm looking at, right? So then I guess I can use that block and to allocate memory that was requested. So it's the simplest approach, doesn't require any explicit lists, because you are just basically iterating through the heap and you're just calculating the next address from the previous in size, right? So now the second approach is an explicit list. So when we keep track of free blocks, so now we're going to have a list of free blocks only, because there is no point in looking at allocated blocks when I'm scanning for free space. I mean, what's the point of iterating, right? So there is no point. I only have to check free blocks. But then it turns out that if I'm going to iterate through this list, that list will become very long at some point. And it's probably not sorted also. So it's kind of hard to tell like which block to pick, right? Because it's just a very long list, and there is no clear strategy that I can use. I mean, I can sort this list, but then I have to whenever free block, I have to find the right place in the sorted list and so on. That's an extra overhead. So another approach is to have a segregated free list. So that means you have multiple explicit lists. So now in segregated free list, I will have certain classes of free list. So I will say, okay, this is the size from this to this is going to be this list. another size from this to that, going to be another list, and so on, right? So I'm going to create multiple lists. And it turns out that it works pretty well. So then you can also sort blocks by size, as I previously mentioned, right? But instead of a list, you can use something more elaborate, such as balance trees, and and hopefully have efficient lookup for free block. Again, there is no guarantee that it's going to be faster than segregated or free list. I guess you can potentially explore that for your project, but it's up to you. So just to kind of also mention for the project, I guess implicit list will give you the lowest score, most likely, right? So, and that's what the textbook shows. Then explicit list probably going to improve performance, but not by much, right? So I guess you can probably get with segregated list to up to like 80 to 90%, right? Of your grade, right? But then it's still not going to get 100%. Even with segregated list. So then you have to use some extra tricks, right, to get 100%. But I'm going to mention them later, right? So once we actually start working on our project and once you implement basic version at the very least, right? So once you get 90% for segregated list, then it makes sense to discuss what you can do to improve performance further. Yeah, but just to, I mean, I guess if you want to start like for the project, you may start with the explicit list if you have time, right? So then if it works, great, right? So then you can switch to segregated list from that, right? So you can basically expand your version and now have multiple explicit lists. If it doesn't work, you can fall back to implicit list for the checkpoint at least, and so just make sure you plan your time wisely. So if you stuck in explicit list implementation, maybe fall back to implicit list for a moment, right? And then at least for a checkpoint version. Okay. So the first method is the implicit list. So for each block, we need both size and allocation status. So we need to say, okay, whether this block is allocated or free. I mean, we can definitely do that by using another word and saying, okay, 1 means allocated, 0 means free. Well, but that's going to be wasteful. So what can we do instead? Well, we can use actually some trick. So remember that blocks are aligned. And in fact, that malloc has a kind of strict alignment requirements that it's even double word aligned. But even let's put aside double word alignment. Let's just say if I'm 4-byte aligned, how many bits, how many low order bits are going to be 0? Any ideas? If I have to be 4-byte aligned. Okay, if I'm 1-byte aligned, yeah, then there is no guarantee that any bits can be 0. Right, so because any bit can be used. But 1-byte alignment is not something that we want to consider because that's not what malloc is going to do, right? Okay, so 2 bytes alignment. 2 bytes alignment means at least 1 bit has to be 0, right? The lowest bit has to be 0. Because if I'm 2-byte aligned, that means I have offset 0, offset 2, offset 4. And if you convert to binary, you will see that the lowest bit always stays 0, right? 0, then 1, 0, then 1, 0, 0, right? And so on. So lowest bit stays 0. So if I'm 4-byte aligned, if I'm 4-byte aligned, so how many bits should be zeros? 2, right? So if I'm 8-byte aligned, 3, right? So it's 2 to the power of number of bits, right? So that's going to be our alignment. So now instead of storing zeros, right? I mean, we are clearly at least 4-byte aligned, actually more than this, right? Because we are double order line. and especially for us when we are using 64-bit CPUs. So we clearly have a lot of low order bits that are set to 0. But at the very least, the lowest one certainly 0. So we can use that one. So instead of storing 0 there, we can use it as an allocated or free tag, right? So we kind of say, okay, is it allocated? Then it's going to be 1. It's going to be free. Then we're going to put 0. So again, size 2 bytes, 4 bytes would normally have 0 there. So now let me recycle that bit in the size to indicate whether that the block is allocated or free. Okay, so when I have to get the size, I have to mask out this bit. So what does it mean, mask out the bit? Any ideas? Okay.
It's like to extract only that bit.
But how do I extract? What operation do I use?
Using, or
Well, if I wanna,
oh, right.
no. If I wanna extract, not set, right? So for setting, I guess I have to use OR, right? But if I wanna extract, so bitwise AND, right? Typically.
Yeah, right.
So you would use bitwise AND, and you will apply a mask. So if let's say lower, if you want to get size, you want to clear the lowest bit, so you want to put zeros there. So you want to restore the original value of 0 for that lowest bit, or you want to extract the allocated free flag. Then you want to mask all size bits. That means all bits except the lowest bit. So only the lowest bit are gonna be extracted. So you will use different masks. Okay, after so we'll have size, payload, and then optional padding. We still can have padding. So let's take a look at this example of a free list. So we have a start of the heap. Oh, by the way, I said that we have to be double word aligned, right? So the payload has to be double word aligned. But seems like I was trying to save some memory, right? And I introduced the header, which is word aligned. So, but how can I make the payload double word aligned if I'm going to be, wasting one word for size, right? So it means maybe I have to do extra padding anyway, right? So seems like I have to waste that word anyway. Or is there any other solution? Okay.
Did you put it at the end?
What do you mean at the end? Well, size I cannot put at the end. By the way, we'll get to that point when we have footer, not just header, but also footer. But normally I still have to have a header. I mean, even when I have a footer, I still have to have a header, because how do I determine the size of the block when I free it, right? So I don't know how large it is, so I cannot reach the footer. But I can always go back by the word size to the beginning of the header and read the size from there. So any other ideas how we can do that? Any guesses?
What was the question?
Well, it seems like I have to be double word aligned for the payload, but the size is only one word, right? So it's not 2 words. So it seems like I'm gonna break the alignment. If my initial alignment is double word aligned, then I have size. How do I get payload again double word aligned? Because I have to then place 2 words.
Yeah.
Well, is there any way to do that? Okay, let's take a look, right? So I can deliberately misalign, right? So the beginning of the header. So it can be off by 8 bytes. Like if my word size is 8 bytes, it can be off by 8 bytes. So that's exactly what happens here. So you have start of the heap, which is initially double word aligned. So initially we'll just wait 8 bytes. It's not a big waste. We'll just waste 8 bytes. If well, I guess it depends on the word size. Let me say that just the word, right? So let's not 8 bytes, because to not make it confusing, right? So we'll just waste one word in the beginning. It's not going to be used. So then the next word is going to be the header. So now after the header, it's again double word aligned, right? So then we have payload. Let's say we have a payload of like in this case, the word size is 4. So the payload of 4 bytes plus the header of 4 bytes, the total is 8 bytes. So remember, the header keeps track of both payload and header size, right? So that's why it's 8. And it's marked as free. So the next block, it turns out that, it's again, it's already misaligned, right? So it's already off by 8 bytes, so I can directly place a header right after this block, right? So now I have this next header. After the header, I'm again double word aligned, right? So the payload is again going to be aligned. So now let's assume we have malloc of 8 bytes. Word size is 4 here. So then it means I have to record 8 bytes plus 4 bytes for the header. That means 12 bytes. But now notice that I cannot place the next block without padding. Right, so I have to have this. In this case, I have to have extra padding at the very end. So because the next block has to be again start at misaligned address, right? Not a double word aligned address. So I have to have this extra padding, which I will also include as size of the block. So now I'm going to have extra 4 bytes in this block. So it's going to be 16 bytes. So 8 bytes were requested by malloc. Then I have 4 bytes for the header, 12 bytes. And extra padding is 4 bytes. So this is how we get 16 bytes. So next block is 32 bytes. I mean the total block size, right? So that's just an empty block. Header indicates 32 bytes. Then we have again 16 bytes block, allocated block. But now the difference is that malloc requested 12 bytes rather than 8 bytes. So now we don't have any padding. It's going to be 12 bytes plus 4 bytes for the header. It's going to be 16 bytes in total. Yeah, so sometimes you will have to insert padding like in the second block. But most of the time, like, I mean, it's kind of random, right? So if it's like whether I'm going to allocate 8 bytes or 12 bytes or 16 bytes, I mean, it's hard to predict in advance, right? So sometimes I have to insert padding, but generally speaking, I'm not wasting memory, right? So I can still achieve double word alignment and yet insert just one word header. Yeah, so it just, you kind of shift the header and make it off by one word. So at the very end, you have some sort of fake block which says that it's allocated in 0 bytes. That can be just just an indicator that it's the end of the heap. Because you can never have block of size 0. I mean, at the very least, it's gonna say that it's 4 bytes in this case, right? Because at the very least, the header itself should be counted. So clearly some fake block, right? And that can be just a marker. Or you can skip the size of the heap and just terminate whenever you reach the end of the heap. Okay, go ahead.
This wouldn't work if the block size were like 1 byte. Not that it ever would be, but it wouldn't work, right?
Yeah, but yeah, so it wouldn't work, right? So for 1 byte, but it would work for 2 bytes still, right? So if you have 16-bit CPU, that's still gonna work. I mean, it won't work for 1 byte because, Well, first of all, that would be like 8-bit CPU is going to go ridiculously small range for integer calculation, right? So, and small amount of memory, I guess, like 256 bytes. That's not a lot of. But yeah. So, but I mean, you can keep, but you wouldn't be able to keep the allocated free status, right? So at least need 2 bytes words. But I guess you can argue for 1 byte for 8-bit CPUs, you would still have double word aligned. So you would still have 2 words, like basically 2 bytes, right? So you still have like 1 bit extra. So I guess it would still can potentially work for 8-bit CPUs. Okay. Because we have double word alignment, right? So not the word alignment. Okay, anyway, yeah, so let's look at the algorithm, right? So previously I looked at this more informally. Let's have a more formal algorithm. Yeah, so first of all, the starting point, let's assume that the starting point is already after this unused space, right? So that's the very first block. So I'm using size T star here because size T typically corresponds to word, right? So in case of 32-bit CPU, it's going to be 4 bytes, and in case of 64-bit CPU, it's going to be 8 bytes. I mean, it's not guaranteed to be like this, but in all reasonable implementations, size T would match the word size. Yeah, so what you're gonna have is that you will scan the entire heap from the very beginning, so from the start to end, so you have the end marker here, so we're gonna terminate, and then you're gonna check, okay, is the block already allocated? How do you check this? So you'll have to dereference the current word, right? So, and mask it with 1. So masking it with 1, what does masking with 1 gonna give me? Put it. Let me try to use them. I don't know if it's gonna record well, but let me try that. Okay. Okay, so we have payload, and now, sorry, not payload, we have the beginning of the heap. We start like we skip the unused portion of that's our pointer P. So now this one points to the header. So if I dereference P, and P, remember that P is a size T star. So it's an array of words, right? So P is going to be this header size, right? So this is, I want to extract whether it's allocated or free block. So how do I do that? I'm gonna have a bitwise AND in hexadecimal that's going to be 0, 0, 0, and 1 at the very end, right? That means I'm gonna clean all bits, all upper bits, and I'm gonna just keep the lowest bit, right? So, and that's the same as 1, right? Right, so this is why we have 1. Oh, you can. Disconnected. Let's. Sorry about this. I think this one is. Okay. And let. Okay, I think it's. Becoming, why is it not? Okay. Okay. So we have E bitwise and with one, right? So that's how we extract allocated free block. So if it's allocated, we want to skip it. So we're just gonna go to the next block. So the first condition, it's that's not the end of the heap. Then the second condition, it's no if it's allocated, right? And or sorry, if it's allocated or the length doesn't match the one that I'm looking for, right? So and if it's smaller than whatever length I'm looking for, then I want to skip. I want to go to the next block. Otherwise, I found the block. If it's a free block and the length is okay, then I can use it. So now, why is that second case they don't mask anything right in here in this algorithm? Well, I would first of all, what would be the right approach to do that? I would have P, and then I would have F, 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 hexadecimal, and then E at the very end, right? So that's going to correspond to 1, 1, 1, 1, 1, and then you have 1, 1, 1, 0, right? Is 1, 1, 1, 0. So this is going to keep everything except the lowest bit, right? So that's going to discard the lowest bit, but going to keep the size. So that, I mean, I technically should use that mask, right, to extract the line. So why I don't use that mask? Okay, go ahead.
Is it because the size, like length is the size plus one, so like you already account for that extra one if it's there?
Well, I would say because it's the first condition is already allocated. So if it's not already allocated, then it must be free, right?
Yeah.
And that means it has lower and lowest bit 0 already, right? Does it make sense?
Yeah, oh, right.
Yeah, so that's either it's allocated, then I'm gonna skip that already, right? Or if it's free, then I'm gonna look at that condition. And so this condition will not be executed if it's allocated, right? So that, yeah, so that means I already have 0 there for the free block. So therefore, it's kind of optional. You can do that, but you know that's unnecessary, right? You'll have that mask, yeah. So now the last line is, what do we do here, right? So we have char star P. So that's the current block, beginning of the current block, plus something weird right now. So we'll look at this, right? And this is how we're going to go to the next block, right? So and then we're going to cast to size T star. So why is it -2? That's not a mistake. Any ideas?
Is that so that the first bit can be 1 and so it keeps the allocation status?
Well, we actually want to discard this bit because we want to just get the size, right? We want to get to the next block, we just want to get the size. Now we have two possibilities. One is allocated block. That's the condition, right? So the first condition that it's allocated block. Or the second condition, it's a free block, but it doesn't match the size that I want. So either way, for simplicity, I'll just have to then now discard the lowest bit, right? So -2, okay, let me ask this question. What is -1 in hexadecimal? Yeah, so any ideas? All ones, right? Yeah, so that's -1, right? And -2 is going to be 1, 1, 1, 1, 1, 1, 0, right? So that's actually this one. So that's the same as -2, right? Yeah, so it's better actually to put -2L probably, or cast it to S size T, I guess, but so just to make sure that it's not doing anything tricky there, because -2 is going to be an integer, not necessarily a word, right? So probably better to have -2L, right? Well, at least in Linux, lon and size T are the same, but not in Windows though. Yeah, anyway, yeah, so that's just a minor thing, right? So, but in general, how do you get -1? Just to remind you, right? If you have 1, how do you get -1? So 1 is 0, 0, 0, 0, 0, 0, 1, right? So to get -1, you invert it. You get 1, 1, 1, 1, 1, 0, and add 1 in two's complement, right? So you get all ones. So just to remind you, right? So the same thing from 2, you can do -2 as well, right? But you know, that's the idea, right? So if you see, I think the textbook also uses -2. So if you see that, don't be scared about -2. Okay, go ahead.
What would happen though if like one payload was multiple blocks? Because if this is going block by block, could there be a block that doesn't have an allocated, like a bit that tracks if it's allocated or not?
No, we always have, all blocks have allocated free bit. And all blocks have size. If it's a free block, we still want to keep size. Yeah, so we kind of split our memory to blocks, right? So now the question is, what's gonna happen if I have a free, if I found some space in a free block? So what do I do with the remaining space? Well, typically I would split free block into 2 pieces, right? One piece is going to become allocated block, and the remaining is going to be a new free block, right? But just smaller, right? So that's the idea. So the first fit approach that is here is going to take linear time, right? So because I have to go through all the entire heap, and you know, it's not going to be great in terms of you know, memory utilization. I can potentially have like I can potentially waste a lot of memory. I will just look at the very beginning of the heap most of the time, right? And may have a lot of fragmentation there. So next fit is like first fit, but we're gonna start where the previous search finished. It can be useful if you allocate like 3, 5, 10 bytes, so you can skip blocks that are not necessary to scan again, right? So if you're trying to allocate 3 bytes and all you had in the beginning 2 byte blocks, you don't need them for 5 byte, right? So you want to skip them as well. So it kind of helps to make it faster. But you know, because we're gonna skip rescanning unhelpful blocks, but you know, it's not necessarily gonna give better result. Some research suggests that can actually cause more fragmentation. So it's not really clear whether it's a good idea. So for best fit, we may try to find the best possible block that, you know, matches most closely to the block that we are looking for. So if you are looking for 2 bytes, perhaps we want to find 2 byte block if possible, or maybe 3 byte block, but we want to keep like 100 byte block alone, right? So even though it still matches, but we don't want to use it. Again, there is no guarantee that it's going to reduce fragmentation even if you use this strategy, because we cannot predict the future. But in general, it helps, but it also makes things slower. So now you have to potentially either order somehow this list, or you have to, I mean, for implicit list, there is no even choice. You have to basically scan the entire heap to find the best possible match, right? And that's not going to be fast.